All right, so in this problem, we're going to show that the hazard function, which is defined by this expression here, and we're going called for to explain why it's called the hazard function to begin with, and why it's the probability density for death at time t, little t, given that a person has survived up until t. So one way to think about this problem is that we have this random variable t, which is time lived, and what we are trying to capture really here is the probability that an individual has lived. Well, we know the conditional here has survived up until time t. Oops. Up until time t, but has lived or going to live just a tiny amount extra. Well, this should be a little t here. Okay, so we're thinking about this little s here as a little, basically a delta t here, right? We're thinking about it as living a tiny amount of extra time. Because we cannot, the probability of a continuous variable at a particular t is always 0, we are adding this extra little amount here. We're trying to capture and ask what does it mean to live this little extra time. So one way now to rewrite this expression, just using Bayes' theorem, is that we have now the two events, the joint events. So we have t greater than equal t plus s, and the conditional here is we know that this individual has lived up until t, and so we're going to transform this expression further by realizing here that this particular event is already encompassed into that one here, right? So you can think about this being something like the following, where we have time here. Well, let me just adjust this here. We don't have to have that one particular. So let's think about what is this t greater than, capital T is greater than little t. Well, that basically means that this individual we know has lived at least up until time t. Sorry about that. So we know this is a little t here. This is the time axis. And we know that this individual has lived up until that. Now, this event here means basically, well, it's the same thing, but we're thinking about it that it is plus a little extra time, s. So this individual is going to live this far, right? So we can see that this probability, this joint probability, is asking for this event here. Okay, so now we rewrite this whole expression to yield the following: plus s, and the denominator is t. Well, the probability here is this expression here in the numerator is basically the CDF at t plus s minus the CDF at t, and this below expression is Well, this is the survival function, but going to come back to it in a moment. So let's just write it down as, sorry, the 1 minus f of t. So this is the complement event. So now up until this expression here, we ask, what do we do next? So how can we transform this expression into the hazard function? I mean, how do we move from this step to that one? Well, this is where we're going to use a little trick, which is, remember what this s is it's a little movement in time, but we're going to ask what happens if we make this s as small as possible, right? It's basically a limit now. So what we're going to do to take the limit is that we're going to divide both sides by 1 over s. Why are we doing this division? Well, we are preparing for taking the limit here, and the limit for any event, or basically the definition of a derivative is the following, which is that we have a expression any sort, and we are taking, well, now there's a clash between functions here, but let me just call this g. So any function that is of interest plus, well, there's another clash here, so sorry about that, let's do an x plus h minus g of x divided by h. This is the definition of a derivative, any function g. So g is any function of interest, and what we're doing by dividing by s here is that we're trying to make this look like this expression so that we can take the limit, and by doing that you'll see that we'll be arriving at this expression here, and that is, intuitively speaking, basically capturing the hazard function. So the event, well, the probability density of living this little extra time, where time being as small as possible. All right, so now that we have divided divided by s both sides, now we take the limit. So here, let me just take another color. We let s go to 0, both sides. Let me move this a little bit, like that. 0. All right, and now if you look up in textbooks, this is actually another way of writing, defining the hazard function. And let's now just proceed by calculating through this and see what do we get. All right, so working with the inner expression here, the limit s goes to 0, okay, like that. Inside, I'm going to divide up this expression so that, and remember, we're taking the limit with regards to s, and the only function here that has an s is actually this function here. The rest are, well, this is another s here, so we need to put these together, and the rest will be considered as constants. So f t plus s minus f of t divided by s. I'm going to move this guy out, okay, and put it here, that, And this, again, this guy here, this expression is just a constant, so we can move it outside of the parentheses here. So let me just copy the following. All right, put it here. We have the limit. S goes to 0. We have this guy outside. And now, by looking at what does this guy mean here? Well, this is actually just the PDF of t. Because, I mean, why is that, you might say? Well, remember, if we take the derivative of any function t, we will get the PDF. That's the definition of the PDF in continuous random variables. And that's what we have here. So we rewrite this whole thing here to be f of t. And now what we're left with is this other expression. And that is indeed, the hazard function that we were supposed to prove. Right? There we go.